Hello, good afternoon, students. Today we'll see the core subject quantum physics, in which unit one we are going to be seeing. So, which unit one is Bohr's theory and line spectra. Okay, Bohr's theory and line spectra. So here in this, uh, if you take a black body, so in the case of the black body, the distribution of energy is in the form of continuous spectrum of a black body you have. So this continuous spectrum of a black body does not explained by the classical theories, whereas Max Planck he introduced a new theory, which is a radiation quanta. He explained the black body radiation continuous distribution. So some quantum theories explained successfully. So later on, we have different theories. They have been came up to explain the quantum arrangement of these energy levels. So here today we'll see, first of all, we'll see about the what is line spectra, then we'll go for the Bohr's theory, then we'll go for the Sommerfeld theory, then we'll see the energy levels which are present in the hydrogen atom, then we'll see about the vector atom model, and then we'll go for Frank-Hertz experiment. Okay, so first we'll go into the line spectra. So what is line spectra and all those things we'll see here. First, we'll see what is line spectra. So if you here, whenever there is a collision of electrons in an atoms with another atoms, some of the atoms will be discharge tube may go into an energy state which is higher than the energy possessed by them. That is nothing but the interaction of these electrons with the atom, and these atoms will be colliding with some other atoms. So at the time, what will happen means the electrons which are present in the energy level, they will be moving into the higher energy level, and later on they will be coming back to this original energy level they are coming. So whenever they are moving from their own original energy level to the higher energy level, and again coming back to the higher energy level to the original level, so there will be radiation is produced in the form of electromagnetic rays. So by losing their what we call original energy. Okay, so that is due to the collision in atoms with electrons and with other atoms. Some of the atoms in the discharge tube may go into an energy state which is higher than the energy possessed by the atom in the normal state. Okay, so whenever they are coming back to the normal energy state, the atoms will be giving up their excess energy and producing the some electromagnetic radiation. So these all, if you see, it is going to perform a spectra. So to measure that spectra, we'll be having some apparatus to measure that spectra. So here we'll see how this will be there, and where the spectra is going to be formed also we'll see here. So we'll have a source here at this point. We have a source, and we have a slit in which the light which is produced here will be traveling parallelly, and it is hitting the prism. And after hitting the prism, they are going to be see on this what we call a screen. So this will be coming through the slit and parallelly hitting this prism. After hitting this prism, this will be going to be form different lines, and this we'll be calling it as a spectrum. Okay. So if you see the arrangement of this measure apparatus which measures the atomic spectra. So here the radiation which is coming out from the source, and it will be directed towards the slit S1, and it will be passes through this slit, and it will be going onto this prism. And this, after going onto this prism, it will be passing out from the prism, and it will be have a photographic plate. So on this photographic plate, the spectrum will be recorded here. Okay. So the electromagnetic radiation which is emitted by free atoms is found to be concentrated at a number of discrete wavelengths here. Okay. Each of these wavelength component is called a line. Okay. Each of this wavelength component is called as a line because of line which it produces on the photographic plate. Investigations on the spectra emitted by different kinds of atoms indicated that each atom has its own what we call characteristic spectrum. That means the spectrum which is produced by the different atoms is different. You are going to be having. So the scientists like Dewar and Leving in the year 1880, they observed that some similarities in the spectra of alkali atoms, alkali metals basically, alkali metals. So they observed that successive pairs of lines in the spectrums are of sodium to be alternatively sharp and diffuse, and they were very closely together, okay, towards the shorter wavelength, okay, end of the spectrum. So when it is having the shorter wavelength, they are very close to each other. You are going to be having. So in the year 1883, some other scientists they have found that there is a difference in the frequency between the components of the multiplet. That is nothing but in a particular spectrum where the same for all similar multiplets of lines in that spectrum. Okay. So if you take this hydrogen spectrum, so hydrogen spectrum actually it is consisting of what H alpha, H beta, H gamma, and so on lines you are going to be have. So these all H alpha, H beta, H gamma, H delta lines which are visible in the hydrogen spectrum. There will be a spacing between the adjacent lines in wavelengths continuously decreases with decreasing the wavelength of the lines. Okay, so there is series limit which is having some 3656 angstroms you are going to be have. Okay, so later on Balmer has been given some formula to calculate otherwise to represent the wavelength of the hydrogen spectrum. So according to this Balmer, so to calculate the wavelength of that, they have given the formula as lambda is equals to 3646 into n square by n square minus 4 angstroms is the formula which it will calculate otherwise to represent the wavelength of the hydrogen spectrum. Okay, so generally in this case we have like n values, like n is equals to 3 for H alpha line you are going to be have, and n is equals to 4 for H beta line, and n is equals to 5 for H gamma line, and so on you are going to be have. Okay, so okay, by substituting all the n values here, we will get the wavelength of the corresponding spectra of the H alpha, H beta, and H gamma, and so on lines. Okay. And Balmer, whichever the formula it has been given like a 364 into n square by n square minus 4, could predict the wavelength of the first 9 lines of the series, okay, known as the time to better than 1 part in 1000. Okay, 1 part in 1000. So a similar empirical laws will be applied to series of lines emitted by other elements also, okay, which are carried out by the what we call Rydberg. So he found that to represent this formula in terms of the wave number, which is given by k is equals to 1 by lambda here. So according to him, the Balmer's formula, which is can be written as a k is equals to wave number is equals to RH into 1 by n square by, that means 1 by 2 square minus 1 by n square you are going to be have. Okay, and here n value should be more than this 2, 3, 4, 5, and so on you are going to be have. Okay, RH is nothing but the Rydberg constant, so which is given by some value, some constant value you have. Okay, so this is what some spectra we have. Line spectra, that is nothing but the radiation which is produced by the electron whenever it is jumping from higher energy level to the lower energy level. It produces the electromagnetic radiation, and this will be the form of a line. So line spectrum it is called. Okay, so then this is about the line spectrum we have. Then we will move to the what we call Bohr's theory. So what are the Bohr's theory? What are the things which has been proposed in the Bohr's theory? We'll see here. Okay, so Bohr's theory. So in the year 1913, Niels Bohr proposed a theory of a hydrogen atom. With this theory, Bohr gave some satisfactory explanation for the Balmer series of hydrogen. So Bohr postulated some four things. So four postulates has been given by the Bohr's theory. So if you see all the postulates given by the Bohr's, the first postulate which we have is he says that according to the Bohr, he says that the electron in an atom moves in a circular orbit about the nucleus under the influence of Coulomb's attraction between the electron and the nucleus. Okay, according to the Bohr, he says that in an atom, the nucleus is at the center, which is positively charged, and the electrons which are there inside of the atom, they will be moving around the nucleus in circular orbits by obeying by the influence of Coulomb's attraction between the electron and the nucleus, which obeys the classical mechanics. That means, according to him, this is the center, positively charged, and electrons will be revolving in circular orbits around this. Okay, in circular orbits. In this manner, they are going to be revolved. Okay, under the influence of the Coulomb's attraction between this electron and the nucleus, which obeys the classical mechanics. So this is the first assumption made by the Niels Bohr, who says that the electrons will be revolving in circular orbits around the nucleus. And if you go for the second assumption, which is proposed by the Niels Bohr, is he says that according to the classical mechanics, you will be having infinity of orbits, which would be possible according to the classical mechanics. So it is assumed that electrons will move in an orbit, and for which the orbital angular momentum L is integral multiples of h by 2 pi. L is integral multiples of h by 2 pi. That is, he says that L is equals to nh by 2 pi. Okay, so that means the electrons will be revolving in different orbitals, in circular orbitals, and moreover, the orbital angular momentum L is an integral multiples of h by 2 pi. That is, h is nothing but the Planck's constant. L is nothing but the Planck's constant. Okay, so this is one more assumption made by the Niels Bohr. Next, third assumption which we have is made by the Niels Bohr, is, whenever the electron is revolving around the nucleus. Okay, whenever the electron is revolving around the nucleus in circular orbit, the electron is constantly accelerating. An electron will be moving in such an allowed orbits. It does not radiates electromagnetic energy. And he says that the total energy of the total energy E is constant, he says that. Okay. As we have said that from the second one, it is integral multiples of the orbital angular momentum. And third one, he says that whenever the electrons are revolving around the nucleus, it is going to be constantly accelerating an electron, which is moved in allowed orbits. And moreover, they are not going to be radiate any electromagnetic energy. And he says that the total energy E will be remains constant. The total energy E will remains constant. So these allowed orbits in which the electrons are revolving are called it as stationary orbits. As called it as what? Stationary orbits. Okay, so this is the third assumption made by the Niels Bohr. And the fourth assumption which he has been given is whenever the electromagnetic energy is emitted, if an electron is moving from the energy level EI, discontinuously changes its motion to so that it moves to in an orbit of total energy E sigma gamma. Okay, so that is the energy is emitted if an electron is initially moving in an orbit of total energy EI, discontinuously changes its motion so that it moves to an orbit which is having the total energy as E gamma. Okay, otherwise EF we can say that. Okay, EI is the in energy level in some other one, and EF is another energy level of the orbit. Okay, so whenever it is radiating, the frequency of that radiation emitted is given by nu, which will be equal to EI minus EF by H. You have EI minus EF by H. So this is the fourth postulate. Here H is constant. H is the Planck's constant. So these are the four assumptions made by the Niels Bohr. The first one is the electrons will be revolve around the nucleus in circular orbits. The second one is the orbital angular momentum of that will be equal to h by 2 pi. And the third one assumption is total energy will be remains constant even it is accelerating. The fourth one is the frequency of the radiation emitted by the electrons is minus EF by H you are going to be having. So if you see these four postulates, the first postulate which it is given, that is the electrons are revolving around the nucleus in circular orbit. This will gives us that the atom is stable. Otherwise, it will gives the information about that the stability of the atom. Stability of the atom. It will gives the significance as a stability of an atom. Why the stability of an atom here it is? As we said that the electrons are revolving around the nucleus, the nucleus is positively charged and the electron is negatively charged. So whenever it is revolving around the nucleus, there will be attraction between the positive charge and negative charge. So whenever they are going to be attract each other, the atom should be collapsed. But it is not happening. It is obeying some Coulomb's forces and it will be revolving around the nucleus. So that's why the significance or the first proposal which is given by the Niels Bohr gives otherwise it tells us that the stability of the atom. Okay, the stability of the atom it is going to be there. That is the first postulate which we have. And coming to the second postulate, it will gives us that okay, the second postulate will give us, otherwise second postulate says or introduces that the quantization of energy of the system. Okay, the second postulate will introduce is that the quantization of energy of the system. So it will give us the quantization of energy of the system. Energy of the system. And coming to the third postulate which we have is it tells actually the third postulate accounts for the stability of an electron which executes the circular motion. So which is against the electromagnetic theory, which is the against the electromagnetic theory. That is what it tells. The third postulate accounts for the stability of an electron executing circular motion. Okay. And those orbits which the electron revolving, we called it as a stationary orbits we have been called. Okay. And the fourth postulate, if you see here, so the fourth postulate of the Niels Bohr it is almost related to the Einstein's postulate that the frequency of quantum of electromagnetic radiation should be equal to the energy carried by the quantum, okay, divided by Planck's constant. That is EA minus EF by H. So these are the four. Postulates which are produced, which are given by the Niels Bohr. Okay. So the now from the assumptions of the otherwise the postulates which are given by the Niels Bohr. Okay. So we will find out the what we call radius of the circular orbit and the velocity of the electron which is revolving around the nucleus whenever it is revolving around the nucleus in different orbitals. Okay, so these Bohr's postulates can be found by comparing the predictions that can be derived based on the postulates, the results of the experiments. So in order to get those, so here first take we will consider that a nucleus which is charged positively, that is generally plus ZE we are going to be called, and the electron is revolving around that in circular orbits. Electron will be revolving around the circular orbits. So this is the radius which we have. Okay, this is the electron which is revolving. So in this direction, and it will change this direction every point of this circle. So the radius of this orbit is RV. Right. So whenever it is revolving around the nucleus, okay. So the Coulomb force acting on the electron, the Coulomb force which is acting on the electron must be equal to the centrifugal force. Okay. Whenever the electron is revolving around the nucleus, the Coulomb force acting on the electron, the Coulomb force which is acting on the electron must be equal to the centrifugal force, which is given by A naught ZE square by R square, which will be equal to the centrifugal force, which is mv square by R here, mv square by R. So here in this, V represents the velocity of the electron, okay, and R represents the radius of the orbit, and the K naught here, it will represent the permittivity of the free space. Generally, the value of permittivity of the free space is the value of permittivity of the free space K naught is equal to 9 into 10 to the power of 9 Newton meter square per centimeter square. Sorry, per coulomb square you have. Okay. So the electron the acting of electron entirely radial. The orbital angular moment of the electron must be given by, because The electron is revolving in a circular orbit. So the orbital angular momentum, okay, orbital angular momentum of the electron is given by L. So which will be equals to this orbital angular momentum, which should be equals to mv r we have, right? So this it should be equals to L is equals to mvr. It should be equals to, from the second postulate, we have nh by 2 pi. This L should be equals to, which is nh cut, we can say nh cut, right? So h cut is nothing but the, what we call h by 2 pi, right? MVR is equals to nh cut, that is nh by 2 pi. And this n value can be taken like n is equals to 1, 2, 3, and so on. Okay. So from this, MVR is equals to nh by 2 pi. Okay. From this, MVR is equals to nh by 2 pi, whichever we have this equation, we can calculate the velocity of the electron, which is given by v is equals to nh by 2 pi mr. Okay, otherwise, nh by mr can write. Now what we'll do is we'll substitute this v equals to nh by 2 pi in this equation, starting equation. So this MVR is sorry, K naught Z square by this equation. Let us say that this is equation number 1 we have. Okay, and the next one is L is equals to MVR, which is equals to equation 2, we can say. So now we'll substitute this value here. What we have is K naught square, so K naught into Z square, which is equals to M R V square, it becomes. It will be MR, and in place of V, we'll substitute this value and s cut by this. So it will be n square h cut square by m square r square. Okay. So which again we can write it as a n square h cut square by m r, we can write. MR get connected square, right? So you can write this value of k naught t square is equals to k naught z e square is equals to n square h cut square by mr, we can write. This is h cut square. Okay. So this way. So from this we can calculate the value of r. R can be given as n square h cut square by m z e square into k naught. Okay. So here n value can take 1, 2, 3, and so on. So here, similarly, this r is nothing but the radius of the orbit already we have discussed. And similarly, we can write the value of v, we can write from this one, because v is equals to nh by 2 pi. V is equals to nh by 2 pi. So which will be equals to the velocity of the electron, which is given by nh. V is equals to z square k naught by z square k naught by nh cut, we can write. MVR is equals to nh by 2 pi. L is equals to MVR, we have already written. So here MVR is equals to nh by 2, V is equals to nh cut by mr we have. So if we substitute, we can get the value of V is equals to this z square into k naught, z square into k naught by nh cut. This we can write. Okay. So this equation r value is equals to nh square by n square h cut square by mz square k naught, whichever we have. So it will represent the radius of the orbit. The radius of the orbit. Okay. And this is proportional to the square of the quantum number. That is the square of the quantum principal number. R is proportional to n square m. So from this equation, we can say that R is proportional to n square, principal quantum. So quantum number, that is principal quantum number we'll call. Okay. So when n is equals to 1, if you take, okay, if you take n is equals to 1, we can get the value of first radius, the first orbital radius, we can get R1, we can get. So actually R is equal to n square, h cut square by mz square is there, no? So there, if you take n is equal to 1, it will be 1 square, and h cut square means h square by 4 pi square into m z e square into k naught. So here, this is the radius of the first orbit, that is circular orbit, whichever we have. So by substituting the values of all up here, okay, by substituting the values of all here, that is h value is 6.6 6 into 10 to the power of minus 34. 4 is constant, pi is constant, 22 by 7, and m is nothing but the mass of the electron, that is 9.1 into 10 to the power of minus 31 kilograms. And Z is 1 for hydrogen atom, and E is charge of the electron, that is 1.6 into 10 to the power of minus 19. And K is nothing but the permittivity, that is 9 into 10 to the power of 9. If you substitute, we can get the value as R1 value, we are going to get it as a 5.28 into 10 to the power of minus 11 meters. Okay. That is the radius of the first orbital we have. R1 is equal to n square h square we have. So this by substituting n is equal to 1, we have got the radius of the first orbital we have got. Similarly, we can find out the radius of the second orbital, which is R2. By substituting 2 here, it will be 4 times of this value we are going to be up. 4 times of this 5.28 into 10 to the power of minus 11 meters. And similarly, if you want to find out the radius of the third orbital, the third orbital will be R3. So which will be n square is nothing but 9 times. Okay, 9 times of this first orbital, 5.28 into 10 to the power of minus 11 meters. Otherwise, we can write it as R3 is equals to 9 times of R1 you have. Okay, similarly, we can write here the R2 value is equals to 4 times of the R1. That means as we are increasing the n value, okay, as we are increasing the n value, the value of radius also going to be changes. For the second orbital, it will be 4 times of the first orbital radius. For the third orbital, it will be 9 times the first orbital you will have. To go for fourth orbital, it will be 16 times of the first orbital you are going to be. Okay. So like this, the radius will be directly proportional to n square you have. Okay. And similarly, as the electron is moving in the circular orbits, it will be having some velocity. So when we take this n value is equal to 1 here, okay, Suppose if you take this n is equals to 1, that is due to for the corresponding first orbital, n is equals to 1 if you take. The speed of the electron can be calculated to be, we have got a 1 by 137 times of c we have got. That is c is nothing but the velocity of light. 1 by 137 times of c we have got. C is the velocity of light. Similarly, if you go for a second orbital velocity will be given by 1 by 2 times of c by 137. And for the third orbital, it will be 1 by 3 times of c, 1 by 3 times of c by 137, and so on you are going to be have. Okay. So the fact that the velocity of the electron is less than 1% of the velocity of light, that justifies by using the classical mechanics instead of for relativistic mechanics of the Bohr's theory. Okay. Suppose this is a velocity we have, and if you want to calculate the total energy of an atomic electron which is moving in one of the allowed orbits, we'll define a potential energy to be zero when the electron is at infinite orbit, infinite distance from the nucleus. Okay, so the potential energy V at any distance r can be obtained by the integrating the energy which is imparted to the electron by the Coulomb's force. Okay, so therefore that V can be written as here V is equals to it is coming from infinite distance to particular value of r, which is equals into k naught into z e square by r square into dr we are going to be. So generally this, if you do the integration and all, if you substitute the limits, we are going to get this value as minus k naught z e square by r you are going to be getting. Okay. So the potential energy is negative here because of the Coulombic force, which is attractive. Right. Similarly, the kinetic energy of the electron, which is given by T, the kinetic energy of the electron T, which is given by general kinetic energy is half mv square we have. So here, if you substitute the values of V and all those things, we are going to get T value as a k naught z e square by 2r we are going to get. V is the potential energy, which we are getting it as a minus k naught into z square by r, and T is the kinetic energy, which we are getting it as a k naught z square by 2r we are getting, right? Now, if you want to calculate the total energy, then total energy is nothing but the combination of the kinetic energy and as well as the potential energy. E is equals to T plus V we have, right? So if you add up these two, that is the kinetic energy and potential energy, we are going to get it as, here we have a k naught z square by r, here we have k naught z square by 2r, and this is minus, this is plus. So if you do those things, we are going to get it as a minus k naught z e square by 2r, which will be equals to minus t. Okay, minus t we have. So by taking the value of r, okay, by taking the value of r, we can get a E is equals to some value, that is by substituting the total energy, we are going to get as E is equals to r capital R by n square we are going to get. R is nothing but the Rydberg's constant. Okay, Rydberg's constant. So this is the energy of the what we call for electron which is present in any of the orbit here. So if you see the energy level diagram for the hydrogen spectrum, energy level diagram for hydrogen spectrum, if you see the different energy level, second, third, fourth, as we are moving, we'll get fifth, sixth, and so on. We'll get in different levels of values of infinite we have. Okay. So if you take this n value, this will be start from 2, 4, and so on to infinite. Similarly, the energy will be energy. If you see, energy will be like a minus 3.35, and next we have for this 1.51. Generally, minus will get minus 0.85, like this. You are going to get here. Okay, this is the energy level diagram for hydrogen spectrum. We calculate the frequency of radiation which is emitted when an electron jumps from an initial state to a final state, which are characterized by the quantum numbers uh, Ni or Nf. Okay, initial energy state is Ni and final energy state is Nf. If we are having, we can calculate the frequency which is produced by the electromagnetic radiation. Generally, that is given by mu is equals to Ei minus EF by H. We have Ei minus EF by H. So here, if you substitute, if you take the Ei value and EF value, that is initial energy state and final energy state, and if you substitute, we are going to get some constant like a, here we'll get the big constant like 2 pi square k naught square and z square e power 4 by h cube into, we'll get some constant here. We are going to get, say that constant as x, which is equal to 2 pi square k naught square and z square e power 4 by h power 3. You are going to get into, we can write it as a 1 by n square f minus 1 by n square I. We can write here. This is the frequency which is produced. So we know that nu by c is equal to 1 by lambda, which is equals to k by lambda here, which is equal to k. So we can get the k value is equals to some Rydberg constant from this new value. From this, we can get the k value in terms of the k value. From this, we can get a k is equals to, we are going to get it as a r alpha z d z square into 1 by n square f minus 1 by n square I. We can get here. Okay. So the value is again 2 pi square k naught square m e power 4 by ch cube. We are going to get. Okay. These are the values which we are going to get by substituting all the values. That is the radius of the orbit we have got, velocity of the electron we have got, and similarly the frequency which is produced by the electron whenever they are jumping from higher energy level to lower energy level. Okay. So here, the Bose theory, whichever we have studying. So the predictions of the Bose theory, which are given by these equations. Okay. So we will analyze the emission of electromagnetic radiation by electron in Bohr's atom in terms of the equations you see here. So the normal state of an atom will be state for which the electron has lowest energy, which is equals to n is equals to 1. The normal state of the atom here, we can get it as n is equal to 1. Lowest energy which is present. Okay. This is for the state n is equals to 1. It is called as a ground state of the atom, the lowest energy which we have. It is called it as what? Ground state of the atom. So electrical discharges of the atom will receive some energy due to the collision. So the electron makes a transition from state of higher energy state to the, this state is called it as what? Excited state. So generally the excited state value should be greater than 1 because n is equals to 1 is the lowest energy state. Excited state means it should be more than that. It should have either n is equal to 2 or 3, 4, whatever it may be, like second, third, fourth, and you are going to have different values. Okay. Next, n should be greater than 1 for excited state, n is equals to 1 means ground state. And next one, the atom emits its excess energy and returns to the ground state. Understand? So when atom exhibits its excess energy and come back to the ground state, in each transition, electromagnetic energy is emitted with a wave number, which depends on the energy lost by the electron. Okay, already we have seen that one we have. And similarly, if the very large number of excitations and de-excitations processes, that is nothing but electrons are jumping from lower to higher and again higher to lower, which take place during the measurement of an atomic spectrum. There are all possible transitions may occur by taking what we call Ni should be greater than Nf. Okay, so here whenever the electron is jumping from one energy level to higher level, suppose if Ni is equals to N, F is equals to 1, Ni is equals to 2, 3, and 4 if we are having, then we'll be calling it as a Lyman series we are going to be called. That means electron is jumping from second energy level to 1 or third to 1 or 4 to 1 or 5 to 1, whatever. So if it is jumping from a higher energy level, third to second, we'll be calling it as a bomber series, which is going to produce. And whenever it is jumping from fourth to third, or fifth to third, or sixth to third, we'll be calling it as a passion series. And similarly, bracket series is from 5 to 4, or 6 to 4, or 7 to 4. And for fund series, it will be from 6 to 5, or 7 to 5, 8 to 5, and so on. You are going to be having. So this, if you see the Lyman series or Balmer series, whatever it may be, which in terms of the level diagram, that is energy level diagram of a hydrogen atom. Okay, so here we'll see here energy level diagram. Right. So in the lowest energy level which we have is N is equals to 1 here, and the more than this is excited state, N is equals to 3, N is equals to 4, N is equals to 5, or N is equals to 6, and so on. We'll have infinite values of N is equals to infinite. So if it is jumping from second to 1, sorry, there should be third, N is equals to 3 also, N is equals to 3, or third to 1, or fourth to 1, or fifth to 1, or sixth to 1, and so on. Then we are going to get this what we call a Lyman series. This is what we call it as a Lyman series. We'll call Lyman series. If it is from third to 2, or from 4 to 2, or fifth to 2, or sixth to 2, and so on, then we'll get the Balmer series. Okay, that is radiation which we are getting. Or from third to fourth, sorry, fourth to third, or fifth to third, or sixth to third, or seventh to third, Lyman, Balmer, and Bastian series, and so on, fund series, and all we are going to be get. Okay, this is the hydrogen atom, which illustrates the production of the spectral series. So this is about the Bose theory. So this Bose theory successfully explained this Lyman bracket and fund series, which have not been discovered at the time of the theory was developed by Bose. Okay. The success of Bose theory lies in the prediction of Lyman and Balmer fund series, which has not been discovered at the time of the theory, which was developed by Bose. So this series later were observed experimentally by Lyman, Balmer, fund, and so on. Okay. So next we'll move to the Sommerfeld theory. So what is Sommerfeld theory? We'll see here. Of the Bohr's theory, if you take, so Bohr's theory, hydrogen spectral lines were well-defined wavelength. According to the Bohr theory, hydrogen spectral lines have well-defined wavelength. But experiments which have been made with the high-resolution spectrographs showed that each of you have like different lines, H alpha, H beta, and H gamma lines. Okay, which is consisting of several very closed lines packed together. So Michelson, he found that H alpha line consisting of two close components which are separated by a wavelength of around 0.013 angstroms. So there are this is known as what fine structure of the spectral lines will call. Okay. So this fine structure of the spectral lines could not explained by this Bohr's theory. To explain this fine structure of the spectrum, so there is another theory which is proposed is the Sommerfeld theory. So what the Sommerfeld theory did is, according to the Sommerfeld theory, he changes some two changes he has been made by the Niels Bohr. So according to this Sommerfeld theory, he says that the electrons will be revolving around the nucleus, not in circular orbits, but whereas the electrons will be revolving around the nucleus in elliptical orbits. Okay, so Sommerfeld introduced the concept of elliptical orbits. Okay, Sommerfeld introduced the concept of that is elliptical orbits instead of circular orbits, which has been proposed by the Bohr. So he says that electrons will be revolving around the nucleus in elliptical orbits. And the second case is the second change which he made is the velocity of the electron moving in an elliptical orbit will be varying considerably at different parts of the orbit. So previously, according to what we call a circular theory of Bohr, electrons will be revolving around the nucleus in circular orbits. But Sommerfeld proposed that instead of the electrons are revolving around the nucleus in circular orbits, they will be revolving around the elliptical orbits. And moreover, the velocity of the electron in circular orbits will be same according to Bohr, but Sommerfeld says that the electrons, whenever revolving around the nucleus in elliptical orbits, automatically the velocity of the electron is going to be changes everywhere. Okay, the velocity of the electron around the nucleus is going to be changes everywhere. Okay, these